Hi, my name is Żukowska, and this summer at CMU, I worked on cherishing every moment, so context expansion for time series foundation models. So, what are time series foundation models? Those are machine learning models that usually leverage transformer architecture and are pre-trained on a very large and diverse set of data. And those models usually take in short univariate time series. And this project is actually about ways how to expand that context, both in the multiple channel dimension and in a longer time sequence dimension. And if the presumption is that if one is able to do that, one is able to capture more intricate relations in the multiple channel dimension and the time dimension and leverage those relations in order to improve predictive accuracy in the downstream tasks. So, just mentioning briefly the experimental setup I started with and ended with. Uh, I leveraged the architecture from Moment, the family of time series foundation models that was actually developed in house here at CMU at the Autumn Lab. For datasets, I sourced them from the time series pile, which the Moment was actually pre trained on. And in order to lessen the computational load that comes with pre training and even training a large model, I introduced Tiny Moment. So just a moment architecture with T5 efficient tiny as the transformer encoder. So getting right into context expansion in multiple variates. This is actually not anything different than just mixing information from multiple channels. So the baseline approach here is just a univariate approach in which we assume that all channels are independent and in which we process multiple channels separate from each other. The other approach I tested is the naive approach, or at least that's how I called it. And it is just concatenating all of the channels, the sequences from all the channels, in one big sequence that produces a very big attention matrix that is quite computationally and memory inefficient. So our approach is actually introducing a compressive memory mechanism that was first introduced in the Infinity attention paper that we actually, instead of employing in an NLP setting as the original one, we employ it in time series. And we also uh, diverge the purpose of originally just applying it for context expansion in length and causal attention. Uh, we employ it for multiple channels by simply reusing the keys and values that are already computed and learned for the dot product attention. Gradient obviously gets propagated from the memory matrix, but those parameters are obviously already there. So the only new parameter that needs to be introduced for our approach to work is the beta parameter that actually weights information from multiple channels from the memory matrix and the univariate information from the dot product attention and merges them accordingly to the beta coefficient. Another thing that we introduce here is that in order to make the retrieval operation more uh, performant here, we introduce channel embeddings right after we add positional embeddings to the input. And before we feed the input to the moment backbone, in which the infinite channel mixer architecture, as we call this, is replicated in each block. So the intuition between channel embeddings is such that similar channels should have similar embeddings. So a query from a particular channel that has a lot of similarities with a certain group of channels should be more inclined to picking up information from the memory matrix relating to those channels. So we verify our architecture by performing experiments on the long horizon forecasting tasks. We actually do not pre-train the model with infinite attention since pre-training non-univariate foundation models is quite computationally expensive, and it is also time expensive. So we only trained them on one particular dataset sourced from the autoformer datasets already included in the time series pile. We test three architectures: univariate, the infinity channel mixer, and the naive architecture. And we ablate channel encodings by including them and not including them in architectures that mix information between channels. So our architecture, the infinity channel mixer with channel encodings, managed to outperform the naive channel mixing strategy in every experiment that we did. And it also managed to outperform the univariate approach, or at least match it, in most of the data sets, but especially not in the ETTH1 dataset, which actually shows to have the least amount of cross correlations between channels. So, moving to the second, a bit less explored dimension of research that we did, we wanted to ask the question if elongating the sequence that is taken in by the model, the maximum sequence, actually improves downstream task performance. And in order to do that, we performed a classification study as well as a forecasting study, in which both we utilized a pre-trained univariate tiny moment, and in the classification study, we use hyperparameter search and support vector machines. And the maximum length that we tested on are multiples of 256. In the forecasting studies, it is the same if it comes to the lookback window. And we also leverage the pre-trained univariate tiny moment, and we only fine-tune a very simple forecasting head on top of the pre-trained tiny moment. And we use the same data sets for this forecasting study as were used before. So, does length matter? No, at least not in classification. The best accuracy scores were actually achieved by the model with sequence length of 512, which is the default sequence length in a moment. And the highest, largest sequence length that we tested actually performed quite poorly. When it comes to the forecasting study, actually we found a very similar thing. That is that for a relatively shorter horizon, mean squared error changes the longer the lookback window is. However, that result is not true if we look at very much longer horizons, such as the horizon of 384 steps in the future. So, having this observation, we came up with a hypothesis of what if the forecasting head that we fine tune is way too simple in order to be able to filter out information that is not necessary to make the prediction task happen. So, having this in mind, this is actually a direction of future work. Our hypothesis is that including a decoder as the forecasting head might actually yield a very palpable and easy performance boost. So, the last thing I would like to leave you with is the taxonomy of interventions that you can make in order to perform context expansion on a time series foundation models. The interventions that we focused on were most attuned with the fine-tuning phase, that is introduction some kind of memory mechanism, introduction of channel embeddings. In the pre-training phase, you can play with different types of tokenization, i.e., different patch lengths, and different strategies of positional embeddings. And during the inference phase, interesting approach would be utilizing some priors that one already knows about the data, for example, for a gating approach. So, to summarize our contributions, we introduce tiny moment to the moment family of time series foundation models, and we develop an infinity channel mixer architecture that actually outperforms the baseline and the naive approach and doing it so more efficiently in a non-pre-trained context. And our third contribution is that we benchmark tiny moment on classification and long horizon forecasting tasks. So this is the end of my presentation. I would like to thank very much all of the people from the Autumn Lab for providing such a vibrant and great research experience to me and all of the other members from the risk cohort that were here with me. Special thanks go out to Manita Goswami, which was my main mentor and that navigating me through the maze of research, to Dr. Nick Gisolfi and to Dr. Arthur Dabrowski, especially for making this experience possible, for invaluable support and contributions. The two other people that need to be thanked is obviously Morgan Grimm and Rachel Burson. Without their organization skills, nothing would be possible here. And thank you once again, lastly, to my sponsors for making this experience also possible. Thank you so much.